तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Good morning. Last lecture was a very heavy lecture where I introduced lots of new mathematical concepts. So, this lecture I am basically going to rework through those concepts, make them a little more sensible hopefully, so that you feel comfortable with all the things I did. So, let me put down what we did. We talked about the magnetic field, and we said that the magnetic field, which is earlier we have got, is mu naught over 4 pi volume integral j cross r12 over r12 cubed dv prime. We took this expression and we identified that this piece r12 over r12 cubed is nothing but minus of the gradient of 1 over r12. This came from electrostatics, because this was found in electric field, this was found in potential. So, if minus of the gradient of potential is electric field and the only difference between the two expressions is this, then it must be true that it is all coming out of the fact that minus of the gradient of 1 over distance is distance over cube of its amplitude. So, it's actually mathematically this is the most important relationship that derives everything else in electromagnetics. So, you take this, you put it in there and you come up with a new result. You come up with a result that B is equal to a new operator that B is the curl of something else. And what exactly is this curl? This curl is nothing but you take the vector product, cross product of two vectors, and you replace one of these vectors, the first one, by the operator gradient. So, for example, instead of saying V cross W, which would be x hat Vy Wz minus Vz Wy plus other terms, now we replace it as curl of W is x hat, this Vy becomes del del y of Wz minus this Vz becomes del del z of Wy plus dot dot dot. So, we are treating gradient, the gradient operator, as a vector, and when you do that, this is now only a function of one variable, one vector field. The other vector field has been replaced by a differential operator. So, whereas this was a function of two vector fields, this is now only a function of one vector field, and it gives you back a vector field. So, it is a vector operator. It takes vectors and gives you vectors, and this operator is called the curl. And what we have seen is that the magnetic field is the curl of something, of a vector field. So, obviously, curl is a very important concept. Now, we also saw the last time that if you took this curl concept and you looked at it closely, what you could say is, supposing I go to a very small loop in say x y, this is at x, this is at x plus delta x, this is at y, this is a y plus delta y. And if you worked out what was loop integral v dot dl for any vector v, any vector field v, what you found, we worked it out, was that it is equal to curl of v times the area. So, in other words, a definition for curl of v is 1 over area loop integral v dot dr, where this loop is a very tiny loop, its size is delta x delta y. I am not going to repeat the derivation because we did that. Now, why this is interesting is we have already seen this somewhere else. We have seen loop integrals in connection with the electric field. So, in electrostatics, we had that E is equal to minus gradient of phi, and the very same derivation that allowed us to write this, which was that integral E dot dl from position 1 to position 2 is a function of 1 and 2 only. That is, it does not depend on how you went from 1 to 2, it depended on where you started and where you ended. So, if you took 1 to 2 and you took 2 to 1 and combined them together, you could prove that loop integral E dot dl was always 0. No matter what loop you took, E dot dl is always 0, which means if you took a very tiny loop, E dot dl is also 0, or curl of E is identically 0. So, in electrostatics, we have E is minus the gradient of phi, curl of E is 0, and divergence of E is equal to rho over epsilon naught. So, this expression, which I have been putting several times, can now be put more mathematically. It is saying the same thing. Saying this is equivalent to saying this, because the definition of curl is nothing but 1 over the area loop integral of E dot dl. So, saying curl of E is 0 and saying loop integral E dot dl is 0 is to restate the same facts, but this is a differential operator, this is an integral, and there are times when the integral is more useful and there are times when the differential equation is more useful. So, we will use both of these. So, you can see that in electrostatics we have got two equations. We have got an equation saying curl of E is 0, and we have got an equation saying divergence of E is rho over epsilon. And we also know something else. We know that there is a unique solution to this problem, that given these pieces of information, given some boundary conditions, there is only one vector field which gives you these answers, which means curl and divergence are enough information to fix E. All right. This is a very crucial statement. We will come back and make it more precise, but it is worth looking at it. We found out that divergence E was something, we found out curl of E is something, we have also found out that E is pinned down, which sort of means that if you have these two pieces of information, you have the vector field, and the statement to that effect is a theorem we will prove later. All right. So, what I want to do today is to take this idea of curl and make it more sensible. It is all very well to write down curl, but what does it mean? So, I am going to take some examples and I am going to try and work out those examples and show you where curl is coming from, and of course, I will also derive curl for non-Cartesian conditions. So, let us take simplest example. I have a uniform vector field, let us say the electric field. Electric field is uniform. So, I know that if I drew a little loop, the loop is tangential to the field only on these two edges. On these two edges it is normal. So, dl dot v or dl dot E is 0. So, I know that loop integral E dot dl, let me call this side 1, this side 2, and let us say that I am going through this loop in this direction. So, it is equal to E at location 1 times delta L minus E at location 2 times delta L. But E is the same at both places, it is a uniform field. So, it is equal to 0. What does curl tell us? Well, to write down curl, I would want to actually give a form for this. So, I will say that the vector field is along the x direction and it has some value E naught. So, let me take the curl of that. Curl of E would be equal to, I will do the determinant, x hat, y hat, z hat, del del x, del del y, del del z. E x is E naught, E y is 0, E z is 0. So, I have to take the determinant of this matrix and that should give me curl. Well, if I take the x component, I have 0 and 0 in one row, so that is 0, x hat times 0. If I take y hat, then I have del del z of E naught, but this side is del del x of 0. Then I have for z hat del del x of 0 minus del E naught del y. But E naught is constant, so it has no derivatives, and so this becomes 0. So, this is an obvious case. We knew that there was going to be no curl and we found that our formula works out all right. Now, let us try to do a slightly more complicated case. It is again a case where we know the answer. I am going to take the field of a point charge. Now, if you take the field of a point charge, what do you expect curl to be? Now, I am not going to work out yet in spherical coordinates because we have not worked out what curl is in spherical coordinates, but I am going to argue for you that curl should be 0. We already know that in a certain sense, because we know that loop integral E dot dl is always going to be 0 for electrostatics. But let us work out that loop integral. Supposing I had a loop that did this. So, the loop is pointing out of the board, that is its face is out of the board, and I am going to try and go around it in this direction, the counterclockwise direction. Well, the electric field is normal to this and this. So, to edges 1 and 2, the electric field is normal, so it does not give me any contribution. To sides 3 and 4, there is a contribution. So, what is the contribution? It is minus ER times dr, because the electric field is pointing outwards, the loop is going inwards. So, there is a minus sign, or I should say ER times minus dr plus here also ER times plus dr. So, it is equal to 0. So, obviously, if I take a loop of this type, this electric field cancels this electric field. The loop is going in opposite directions, but the electric field is the same. If I take a loop that is on the surface of a sphere, well, the electric field comes out of the sphere. So, it is 90 degrees to the loop at every point. So, clearly it is just 0 times r d theta plus 0 times r sin theta d phi. So, it is 0. So, that particular loop does not give me anything. Now, I can look at the loop that corresponds to a vertical direction rather than a horizontal direction. But because this is spherical symmetry, if I look in the vertical direction rather than the horizontal direction, it is still the same picture. That is, if I cut the 3-dimensional picture vertically, I will still find that I have got a charge in the middle and I have got electric field pointing in all directions. So, no matter what I do, I am getting integral E dot dl is 0. As I said, this is what I expect. Electrostatic fields cannot give me E dot dl non-zero, but it is good to always draw these pictures and make sure. Now, let us go for a case where there is curl. Let us try and understand what sort of field can give me curl. First, let me again look at a case where it does not give me. I am going to go to Cartesian. This is x, this is y, and let us say I have a field which is uniform in y and growing. What sort of field can this be? For example, supposing you have a mountain and there is water flowing and you are looking at this water velocity of the river. So, here it is slow, here it is speeding up, here it is very fast. So, the water is flowing faster and faster. Is there curl? Well, you can draw your dotted loop. There is nothing on this side, there is nothing on that side, because they are 90 degrees. What about these two sides? Well, in these two sides, you can do an integration. That is, there is a net velocity here, there is the same net velocity here. So, when you do the integration over this side, it is equal in magnitude to the same integration done on this side, because it is the same vector at both points. But your loop is going this way here and is going this way here. So, whatever you gain from your E dot dl on this edge, you lose on your E dot dl on this edge. So, loop integral V dot dl equals 0, which means curl of V equals 0. Now, from the various examples we have seen so far, it should be fairly obvious what you require for curl. What you require is a variation in the field which is at 90 degrees to the field itself. So, that is the kind of example I am going to draw next. Let us look at it. Again, x, y. I am going to take a field which is weak and it is getting stronger, and it will get stronger and stronger as you go further. Now, what happens? Well, let me draw my loop. As usual, this side and this side cannot contribute because the field is 90 degrees to dl. So, E dot dl goes to 0. But now I have sides 1 and side 2, and let us say that I am doing my integration this way. So, I have integral over 1 E dot dl plus integral over 2 E dot dl. Now, clearly in the region 1, E is larger, right. So, it is dl times E in 1. Here it is plus minus dl E at 2, but E at 1 is not equal to E at 2. E at 1 is a large vector, E at 2 is a small vector. So, these two are not equal, this is bigger than this. So, even though they are tending to cancel, the cancellation will not happen. You will get dl times E of 1 minus E of 2, and it is not equal to 0. This is a case where you have curl. There is a kind of an experiment you can do, which is mentioned in every textbook. What you can do is imagine that you made a paper boat and you put it into this vector field. Just imagine it in your mind and you watch what happens to that paper boat, or better than a paper boat, put a flower. So, you can see that the side of the flower at the top is being dragged fast. The side of the flower here is being dragged back slow, is being dragged forward slowly. So, what happens is one side of the flower gets pulled further. The result, the flower starts rotating, and the rotation of the flower is nothing but the presence of curl. Now, in order to fix this in your mind, I am going to take an actual expression for this field. I am going to say that I have, say, an electric field, or y an electric field. I will choose a magnetic field which is equal to, it is in the x direction, but its magnitude is y. So, it is 0 at y equals 0, and it keeps growing and gets bigger and bigger. So, that is very similar to this field. Now, I want to take the curl of this field. So, what do I get? If I take the curl, it is the determinant of x hat, y hat, z hat, del del x, del del y, del del z. The x component of B is y, the y component of B is 0, z component of B is 0. So, this is the determinant I want to calculate. Let us do it. X hat is the determinant of this 2 by 2 piece is 0. Y hat, the determinant of this 2 by 2 piece is del y del z minus 0, and the z component is the determinant of this piece, which is 0 minus del y del y. Well, del y del z is 0, because if I move in the z direction, the y coordinate does not change. That is the meaning of coordinate systems. If I move along one coordinate, the other coordinate is not changing. So, this is 0, but del y is equal to 1. If I move unit distance along y, the value of y changes by unity. So, the slope of y with respect to y is 1. So, it is equal to minus z hat. So, curl of B is not 0, and in fact curl of B is minus z hat. Does that make sense? Well, you can see, take a screwdriver in your right hand and try to screw in the direction that you think the rotation is going to happen. Imagine your flower, put it into this field. You know that the flower is going to rotate this way, it is not going to rotate the other way, it is going to rotate clockwise. So, if you take a screwdriver, rotate it clockwise, it will go into the board. But now, what is z hat? Z hat is x hat cross y hat. That is, the unit vector along z is the unit vector along x, vector product unit vector along y. So, I take my screwdriver again, but I now need to turn it from the direction x to the direction y. Can I do it this way? No, I have to do it this way, because I have to bring it from x to y. So, the z direction is coming out of the board, curl is going into the board, and that is why we have the minus sign. So, this is a case of a vector field that has curl. Now, of course, the common examples of curl are not in Cartesian fields at all. The commonest example that you would have seen is your wash basin. You have water coming from a tap, and the water fills up, and then you allow it to drain. So, what does the water start doing? Water starts circulating and then comes out of the drain. It comes through the pipe and goes to the drain. This is a classic case of circulation. So, it is these fields that were first the reason for calling it curl, because you could see that the vector field was curling round and round. There is no curl in a Cartesian field. It just so happens that the mathematical operation gives you curl, but when people first invented the operator, they were thinking of eddies, they were thinking of whirlpools. So, let us look at a whirlpool kind of field and see what kind of whirlpool field has curl and what does not. So, I am going to draw now in r theta, z is out of the board. So, this is my x, y. So, some general direction is r and theta is this direction. Now, if I want to draw a circulating field, I am going to draw arrows like this. Now, the question is, what kind of field of this type would have curl and what would not? So, I am going to guess, well, what about, if I look at this, I will say, what about a vector field V which is equal to theta hat? So, it's not growing in amplitude, but it's still always rotational. So, for this we have to draw our E dot dl or V dot dl. So, we make a loop. I have made a loop where the sides are 45 degrees and 0, going from r to r plus delta r. Well, you can see that the pieces at constant r are the ones that are parallel to the field. Pieces that are along constant theta are 90 degrees to this field. So, these two sides will not contribute, exactly opposite of electrostatics. In electrostatics the field was radial. Now, we have got fields that are in theta. But what about these two fields? This distance is r delta theta, where delta theta happens to be 45 degrees in this diagram. This distance is r plus delta r delta theta. And now I am going to do, I have to choose a direction in which I will go around. So, let us say I chose that direction. So, what will my loop integral E dot dl be, or sorry, V dot dl be? There is the piece at r, the magnitude of V is 1. So, it is 1 times r delta theta, and there is the other piece which is plus 1 times minus r plus delta r delta theta. The minus sign comes because theta is in this direction, but dl is in the opposite direction. So, I get delta theta times r minus r plus delta r. R's will cancel. So, I get minus delta r delta theta. Now, to get curl, I must divide by the area of this object, of this loop. What is the area? Area is equal to delta r times this length, which is r delta theta. So, it is r times delta r delta theta. And if you look at the curl, it has only a delta r delta theta. So, curl of V is equal to, well, I put a minus sign. So, curl of V in the direction that is normal to this, which is into the board, okay, n is equal to minus 1 over r times r delta theta divided by r delta theta. What did I do? This is the value I have. I multiplied and divided by r, and the area is r delta theta. So, these two cancel out. So, I get minus 1 over r. So, the amount of curl is minus 1 going into the board. Well, as it so happens, if you look at r hat and theta hat this way, z hat is coming out of the board. So, if you wrote out what curl of V is, it is actually equal to plus 1 over r in the z direction. So, this is a field that does have circulation. If you put a flower in here, what is going to happen? The flower will, as it moves, will see this velocity, it will also see this velocity, but it is moving much less here, moving much more there, and as it moves, it is going to start rotating. And what you find is that this has a much greater effect because it is applied over a much longer distance. This has a much less effect, and therefore, the flower starts rotating, and as it rotates, it shows up that there is a curl. So, we have seen that there is a circulating field with curl. Are there circulating fields without curl? I am going to take a field which is large near the origin, but gets smaller as you go further away from the origin. And gets smaller still. So, the particular field I am going to look at is V is equal to 1 over r theta hat. Now, what happens? If I do my loop integral, the same thing that I did earlier works, except that I get, if I draw my loop, I find this is, let us say, 1 and this is 2, V of 1 times r delta theta plus V theta of 2 times minus r plus delta r delta theta. That is just the definition. The sign comes from the fact that V is always pointing this way, but dl is pointing the opposite way. But V theta is now 1 over r. So, it is equal to 1 over r times r delta theta minus 1 over r plus delta r plus delta r delta theta. You can see the r cancels out, the r plus delta r cancels out. So, you get delta theta minus delta theta equals 0. So, this is a case, a field that is getting weaker as you go out, specifically as 1 over r. This is a field that has 0 curl. So, it is not true that every circulating field has curl. It is not true that every straight field does not have curl. Curl comes from your imagination that you put in a round object and does it start rotating. If it starts rotating, it is curl, curl is present. If it does not rotate, curl is absent. Now, you can't keep on drawing E dot dls. Well, actually you can, but mathematically you would like to formalize and find out a mathematical way of calculating what curl is. Your appendix A in your textbook give you the answer. Supposing you have, I have introduced this idea before, but I will repeat it. Supposing you have, instead of x, y, z, I am going to call them u1, u2, u3, and dl along u1 is h1 u1 delta u1, this will be h2 delta u2 and h3 delta u3. Let me give examples. For Cartesian, h1 equals 1, h2 equals 1, h3 equals 1, u1 is nothing but x, u2 is nothing but y, u3 is nothing but z. For cylindrical, u1 will be r, u2 will be theta, u3 will be z. If you look at distance along r, distance along r is nothing but dr. So, h1 is 1. Distance along theta is not d theta, it is r d theta. So, h2 is equal to r. Distance along z is dz. So, h3 equals 1. If you go to spherical, your u1 is r, your u2 is theta, and your u3 is phi. Distance in spherical coordinates along r, dr. So, h1 is unity. If you go along theta, so that means this is my axis, I go on a great circle. So, if I go on a great circle by a distance subtended by delta theta, this distance is r delta theta. So, h2 is equal to r. If I go in the phi direction, then I am going on a circle that is at fixed latitude, and this is the angle delta phi. This distance is delta phi times this radius, which is r sin theta. So, h3 is equal to r sin theta. So, you can do it for any coordinate system, but these are the three common coordinate systems. So, these are the three things you should know. Now, in terms of this notation, we have already written out what gradient was. Gradient of any I should not use phi, gradient of any scalar field is equal to 1 over h1 del f del u1 along the direction u1 plus 1 over h2 del f del u2 along u2 plus 1 over h3 del f del u3 along u3. In Cartesian, these three are missing, but in cylindrical, for example, you have 1 over r del f del theta. So, that is where the 1 over r came from. Similarly, we have done it already for divergence, but now I want to talk about curl. The derivation is easy, but I am not going to give it. It is more useful to know the answer. Answer is, if you write down what curl is, it can be written as 1 over h1, h2, h3, determinant of h1 unit vector along u1, h2 unit vector along u2, h3 unit vector along u3, del del u1, del del u2, del del u3, and h1 v1, h2 v2, h3 v3. So, all these metric coefficients, these things that relate change in coordinate to distance along the coordinate line, come in this fashion: 1 over h1, h2, h3. This is like a volume factor. Then your unit vector now has a h associated with it, because when you what does it mean to go one unit in that direction, and your function itself is also multiplied by h1, h2, h3. Let us work it out for cylindrical coordinates and spherical coordinates. So, what you will get is, for cylindrical, 1 over h1, h2, h3 is 1 over r, determinant r hat, r theta hat, z hat, del del r, del del theta, del del z, v r, r v theta, v z. That is what it is. I have just substituted h1, h2, h3 to get it. So, what does it become? If I take the r hat component, it becomes 1 over, or I will say r hat over r del v z del theta minus r times del v theta del z. Then if I take the theta component, the r and the r cancels out. I get del V r del z minus del V z del r. And I am going to write the last component up here, plus z hat divided by r times del del r of r V theta minus del del theta of V r. So, this is just the expression, there is nothing magical about it, you can in fact derive it. What is useful is it in fact allows you not to keep thinking of E dot dl. I do not know if that is a good thing or a bad thing, because the E dot dl or the V dot dl is the correct fundamental definition of curl. So, if you can keep little loops in your mind, you can never go wrong, and this expression is nothing but little loop with its face pointing along z, little loop with its face pointing along r, and little loop with its face pointing along theta. Each of these is nothing but loop integral V dot dl divided by area, that is all it is. So, if you could directly do it, you do not need this expression, but you can take it as an problem and just verify that the previous examples we have done, they all fit and give you the correct answers that we have already derived from loop integral. For example, if you take 1 over r theta hat, so what happens? This V theta is 1 over r. So, 1 over r times r is 1, there is no V r, there is no V z. Obviously, if you have a constant vector and you are taking derivatives, answer is going to be 0. So, a velocity vector with 1 over r theta hat has 0 curl. If on the other hand your V theta was constant, then this would have been r, because constant times r. Now, if you do the expression, what you get is d dr of r. This term survives, this goes away, and all the others are 0. So, you get one term which is d dr of r, and it is along the z direction. So, what you get when you work out, this term survives and you get z hat over r times the r derivative of r, which is 1, which is what we got earlier. We found that it is in the plus z hat direction and its magnitude was 1 over r. There is nothing surprising about any of this, because the loop integral concept is behind this formula. The earlier derivation was more fundamental than this. This is only a formula. If you actually could put loop integrals and do it, that is the most correct way of doing it. All right. Okay, I hope you are now a little more comfortable with what curl is. Now, let us get back to electromagnetics. We had already seen electrostatics told us curl of E is 0, and we had worked out that B is equal to curl of A, where A was equal to mu naught over 4 pi volume integral J r prime dV prime divided by mod r minus r prime. This is what I call R12, and this is A at r. Now, we would like to know the properties of B. We say that B is equal to curl of A. So, the first thing we would like to do is to work out what the divergence and curl of B are, because we already know that when we wrote down divergence of E is equal to rho over epsilon naught, somehow we managed to fix E. We got a unique answer. So, we would like to know what the divergence and curl of B is. So, when we take the divergence of B, it is actually the divergence of the curl of some vector A, and you put it into your matrix, and I am working in Cartesian coordinates x hat, y hat, z hat dot divergence. So, the x hat, y hat, z hat gets replaced by del del x, del del y, del del z, this is what you get. It is the determinant of a matrix with two identical rows. Now, those two rows are actually differential operators. So, it does not really mean anything to say there are two equal rows, but if you look at what will happen, you will see that if you choose to expand along the third row, then you will get A x is acted upon by del squared del y del z minus del squared del z del y. Similarly, if you take A y, you will get, you will have to check the sign, I think it is del squared del z del x minus del squared del x del z A y, plus for A z it is del squared del x del y minus del squared del y del x acting on A z. And from your mathematics you know that del squared del y del z is nothing but del squared del z del y. These two are the same operator. So, this goes off, this goes off, this goes off. So, it is equal to 0. So, the divergence of B is 0 whenever B is a curl, and we have derived that B is a curl. So, we have got one as one of the two relations we want. We know what the divergence of B is. Now, we have one other fact, which is that if you look at how we derived for electrostatics, that loop integral E dot dl was 0, actually you can easily show that curl of the gradient of anything is 0. It comes from the same idea, that is the curl is nothing but x hat, y hat, z hat, del del x, del del y, del del z, del psi del x, del psi del y, del psi del z. So, if I take say the x component, it is equal to del squared psi del y del z minus del squared psi del z del y plus two other terms. And once again, because del y del z is the same as del z del y, this is 0. So, there are two very important statements that are there in vector analysis, and they are crucial to electromagnetics. One is divergence of any curl is 0 and curl of any gradient is 0. This is why curl of the electric field is 0. This is why divergence of the magnetic field is 0, because B is curl of A, E is gradient of phi. Now, what does this mean? We already know that B is the curl of something. So, supposing I said B is curl of A, and then I look at this, I can say B is also the curl of A plus gradient of something, because curl of the gradient of anything is 0. This will just give me 0. So, the value of A is not unique. We have given an expression for A, but that expression is not unique. In fact, there are many vector fields A whose curl gives me B. Now, if I take the divergence of B, I get 0 because it is curl. I mean, it is already a curl. But if I take the curl of B, it is going to be equal to the curl of A plus grad psi. Now, I am not going to give you the vector algebra right now, but it turns out that this is equal to gradient of the divergence of A plus grad psi minus del squared of A plus grad psi. And because of this, you can use grad psi to adjust the values that are present here. And by doing this, we will be able to put this A in the correct form, where curl of B will have a useful value, divergence of B is 0, which fixes B as a unique vector field. It is a bad place to stop, but I will continue next time and complete this topic.